Here we go, part 2. We're going to talk about elliptical orbits and other types of orbits. So elliptical orbits. All right, oops, oh, that's off the, there we go. So here we go, an ellipse rather than a circle. So what's the difference with an ellipse? That is kind of terrible. Ellipse has two what are called focal points or foci rather than one center. All right, and so here we go. We should know something about our ellipse from our math classes. So if this is focus 1 and this is focus 2, or F and F, this is the center point, C. What we're going to say here is Kepler's first law, which we should have learned last year, is that for objects that are orbiting in elliptical orbits, like all of the planets, the sun is actually at one of the focal points. So that means that when our planet is orbiting around here, and there's our planet going around, that planet is going to be at a variable distance from the sun, right? Because this is going to be the vector for FG, right? This is going to be my FG vector, always pointing directly towards the sun, meaning my radial distance is variable. So the main thing with elliptical orbits then is that FG is not constant for this object that as it goes around the sun. Okay, so let's just go back a little bit to the math of an ellipse just to define some things. First, here's my focal distance 1, here's my focal distance 2. Hopefully you remember a couple of things. I'm going to call this distance here the major axis. The major axis has a length of 2a, meaning the distance from here to here, which is called the semi-major axis, has a length of a. This distance here is called the minor axis, has a length of b, 2b, excuse me, and then half that distance is b, so that's the semi-minor axis. The distance from the focus to the center of the ellipse is called c, right? And it's called the focal distance. So technically the distance from focus to focus is 2c, and the distance from the center out here is c itself. So what you should have learned about the ellipse is that there is something called the eccentricity of the ellipse, or little e, and the eccentricity of ellipse is merely c over a, right? And all that says is how elliptical is my ellipse, how stretched out it is, because that's all an ellipse is a circle that's been stretched along one of those axes, such that if c is equal to 0, meaning the two foci overlap, you have a circle, right? And therefore all the radial distances would be the same, right? Here, my radial distances are going from anything from the longest bit to the shortest bit. So let's define those distances as well. We're going to call the shortest distance between the sun and the ellipse, we're going to call that RP. RP is going to be for the perigee distance. It's sometimes when the sun is the thing at the center, it's called the perihelion, right? Helion for sun. Peri means closest. So a perigee is a point of closest approach. Perihelion, point of closest approach to the sun. Whereas this distance here is going to be RA. RA is going to be called, or that point is called the apogee or the aphelion point. So aphelion. Ap is just a nice way of saying farthest from. So it's a point of furthest recession, or that you are the furthest from the sun in this case, right? So that's the largest distance, that's the smallest distance. Therefore, what we're going to say here is that A, this semi-major axis here, A, is just equal to RA plus RP over 2, right? It's just that distance plus that distance divided in half. There it is, okay? And sometimes this is called the mean orbital radius, rather than, because we want to acknowledge that the radius is not constant because I'm going around an ellipse. So we tend to talk about elliptical orbits in terms of their semi-major axis or their mean orbital radius. So that's just a little bit about the geometry of an ellipse. Now, here's the important consequences of the fact that that happens, that that happens, that the orbit is elliptical. So once again, focus 1, focus 2. Here's my object here. I'll just draw it in 4 different locations. And here's my sun. Let's draw in our major axis and our minor axis. There we go. And so if I'm looking at the speed of the object, so here would be the perigee velocity, here would be the apogee velocity, right? And here would be 2 other different velocities. Let's actually not draw them there and there. Just I'll draw it here. Here's some sort of random point. Let's call this point 1, right? V1. And here's some random point, say V2. Okay. So what's happening here? Well, we can think about a couple of different ways to talk about associating the points, because what's no longer going to be true here is that the speed of this object is not going to be constant as it goes around, right? It can't be constant because the force of gravity is not constant on it. So that equation that we had for V sat equals the square root of big G m over r was contingent on the radius being constant, right? So we can't use that notion here. So how do I figure things out here? Well, the first thing we can figure out is, where do you think this thing is going fastest? Hopefully you're thinking here where the force of gravity on it is the strongest, and that is true. The nice thing about this system is I can say that energy is conserved in this system, which is really helpful. Why can I say energy is conserved? Well, the work done by non-conservative forces is equal to 0. Of course it is, because the only force here doing work is the force of gravity, right? And gravity is a conservative force. So for an object in orbit, energy is conserved. That means the energy at one point is equal to the energy at another point, right? So that means that the kinetic energy at that point, so 1/2 mass of the satellite v at 1 point squared, minus, right, because the potential energy, big G m of the satellite, m of the thing at the center, all over r at position 1 has got to equal 1/2 ms v2 squared minus big G ms m boom over r2. So just in terms of the math here, we can kind of think, okay, when r is small, that means that this is going to be larger, right? A larger number. And when when r is bigger, this is a smaller number, right? But then remember, the negative signs, I'd be adding this to the other side, meaning that V1 has got to be bigger than V2, because I'm going to have 1/2 ms V1 squared is equal to 1/2 ms V2 squared plus some factor, because that number is bigger than this number, which would mean that this has to be bigger than this, meaning it's going faster when it is closer, right? Or you could remember Kepler's second law, which said that equal areas and equal time, which is why you're going faster when you are closer, right? That's just another thing that we learned. But conservation of energy. But that's really awkward because I've got V squareds, I've got R's, it's a big mess. I'd have to know something about both locations and say the distance and then calculate that. But that's a lot of work. Thankfully for us, something else is going on. If I look at the force of gravity here, Fg, right? And I look at that radial position, there's my R vector, there's my Fg vector. You will note that the R vector and the Fg vector are anti-parallel to each other, meaning that the angle that they form, if drawn concurrently, is going to be 180 degrees. And that's going to have a consequence. And that consequence is that that force of gravity vector is not causing a torque on this. So the torque due to gravity here is equal to 0 throughout this, because torque, if you remember, is going to be that R cross F, which was equal to, or the magnitude of this is equal to the magnitude of R, the magnitude of Fg, times the sine of the angle between them when drawn concurrently. That's what would end up going to 0. So there's no torque, meaning that the net external torque on any satellite in orbit is equal to 0. So if the net external torque on any satellite in orbit is equal to 0, what that means is that the angular momentum of this thing at any two positions has to be equal. So if I look at two positions, then I know that the mass of the satellite at that position, and we're treating it as a point mass, by the way. So L for a point mass is going to be mvr sine theta, where v is the speed of velocity of the object, r is the length of that orbit at that point, and theta is the angle between the v and the r vector. mvr at one position, so some initial position, is going to equal msat v final r final. Oh, I forgot my sine thetas here. Sine theta I, sine theta f. Yes? Now, here's the great thing. Let's look at two very specific positions to compare. If I compare the apogee and the perigee, notice here, that's my r vector for the perigee, and that's my r vector for the apogee. So the angle between these two when drawn concurrently is 90 degrees, meaning that sine of 90 is going to go away, mass of the satellite goes away. So if comparing the apogee to the perigee, we know that the angular momentum at those positions are the same. So the speed at the apogee times the distance from the apogee is going to equal the speed of the perigee times the distance to the perigee. Boom. That kind of tells you right there that when you're further, RA is larger. That means VA has to be less in order to make it up. So I'm going faster and closer, further and slower. So this only works at comparing the two specific positions about the apogee and the perigee, because the radial vector makes a 90-degree angle with the velocity at that point. At this position here, it's a little bit messier because, say, there's V2 and there is the R2, and therefore theta 2 is not 90. It's a little bit messier to look at it in other places, and don't worry, we're not going to. Okay, so there you have it. We can look at elliptical orbits by looking at conservation of energy as well as conservation of angular momentum. So that's really interesting there. So if I look then back at this equation there, the total energy of an object in an ellipse is going to be either of these sides. And so here's what it comes down to. Let's talk about the possible orbits that can happen. So here is a planet that we're orbiting. I can have an ellipse that looks like this, or I can have an ellipse that looks like, I don't know, like that. Or I could have something in the center, which is, a circular orbit. Okay. Now, all of those orbits are closed. We also have other things going on. There's plenty of things in this universe that do flybys by the planet, right? That they go by the planet and you have something that looks like that, or maybe something that looks like that. Hopefully what you're noticing here is that all of these things are conic sections. Yes? So why does that matter? It matters because we have two basic types of conic sections here. We have closed conic sections, the circle, and we have open conic sections, which are the hyperbola and the parabola. The total energy for any closed orbit is always negative, right? That's where the negative sign means. A negative total energy means a bound satellite. The total energy is equal to 0. That's for an object in a parabolic orbit, and the total energy is greater than 0 is for a hyperbolic orbit. Okay. Now, why is that important? Well, it's important because there's a problem that's called escape velocity. If I want to escape from the gravitational attraction of a planet, I have to go from something that's in a bound orbit or from a bound position out to the place where I'm no longer bound. And so no longer bound means that the orbit or the path is no longer correlating with an energy, total energy that is negative, meaning I have to correlate with a total energy that's positive. So in other words, I can figure out how fast I need to move away from a point, because if I'm trying to be bound, I know that the total energy has to be negative, so that 1/2 the mass of your satellite times v of the satellite squared has to minus big G, mass of the thing at the center, mass of the satellite, all over r, that position I'm starting at, has to equal 0. Because I want to find the minimum speed that allows me to get unbound. And so notice that cancels there. And I can find out that the satellite speed at that point has to be the square root of 2gm, I crossed out the wrong m there, m of the thing at the center over r. And that is sometimes called the escape velocity. Okay, and so that's an escape velocity from a position r with respect to the center of a planet. Okay, and so that's why it was important that we had those total energies that were negative. That negative total energy means in a bound orbit. All right, so there you go there. The one last sort of weird thing that we need to talk about is going to be what happens if I drill into the center of the Earth. I know, kind of odd there. Right? And so like if I make a tunnel into the center of the Earth, what happens there? Now, if looking at this equation, Fg is equal to big G m1 m2 over r squared, one might say, well, if I am inside the planet, my r got smaller, therefore Fg got bigger. The problem is that's no longer true. This equation is presumptive of being outside of the object. Because remember when I said before that really this equation is the integral. We're adding up the contributions of all the masses that are pulling on you. If I look at this situation here, all the mass to the left of that dotted line is pulling this object inwards. So like this little bit of mass is pulling it like this. This little mass is pulling it like this. This little mass is pulling it like this. This little mass is pulling like this. But simultaneously, this mass is pulling it, trying to get it out, right? And so what ends up happening here is that as you go from the surface of the Earth towards the center, the force of gravity on you actually decreases, meaning that this can't be the equation for it once you're inside the planet. So if you think about it, what does it need to be at the center of the planet? Well, at that point, you're going to be pulled equally in all directions outwards. And the force of gravity there is 0. I'm not going to get into it, but this is outside the planet. Inside the planet, the force of gravity is actually linear with r, right? It is actually big G mass 1 mass 2 over r cubed, where r is the radius of the planet itself. You'll notice there at little r equals to big R, when I'm at the surface, that collapses to this equation. And so that is inside. But you notice here that if I were to draw this magnitude, that I would have a linear relationship and then it would go inverse squared die off. Now, if I was actually doing this with a vector, right, all these things would have negative r hats, fg, and so it would actually look like that, where that's asymptotic then on the r-axis eventually. So it's a little weird variant, but thinking about gravity actually getting weaker as you go inside, every once in a while, they throw out a multiple choice question about that. So that kind of wraps up all of the stuff that you need to know for the AP exam in terms of universal gravitation.